Hello everyone, welcome back. In today's video, we would like to cover multivariable optimization. So we obviously covered in single variable calculus optimization problems. So we are going to today tackle optimization problems in the same way we would for single variable calculus, except we'll do it for multivariable now. We do have a bit more nuance with multivariable, and we're going to explore that with the Lagrange multipliers in the next sort of topic set. But for now, we want to just keep going on kind of our maximum and minimum shtick and discuss that in the context of optimization problems. So we're just going to do a super quick one today, but as you can see, it's generalizable, and we use everything that we used in the previous examples in order to build off of that, so you can really do this for any problem that you like. So let's get started with some multivariable optimization. We're just going to do one example today. I would like us to consider a box without a lid made from 12 meters squared of wood. Find the maximum volume that this box can be, given the constraint of 12 meters squared of wood to build it. So we can imagine that we have a box, or we have kind of a side here to our box. Then we've got some sort of depth to our box. And then, of course, we've got some height as well. And so what we can do, and this is open, so this is not a side, this is just something else. So if I want to find the volume of the box, I can find that with this equation that we learn in elementary school. So V is going to be a function of the length of the box, the width of the box, and the height of the box, right? So we are going to make, we're going to denote this as our length, this as our width, and this as our height. Okay, so what we can do now is we can generate an equation from this. So we want to find the surface area of the whole thing, and we can do that by just adding up all of the areas of the rectangles. So we've got length times height, so that gives us this rectangle, but we've got one on the other side, so we multiply that by 2. So we've got 2 length times height. Then we want to find this area here, but we've got another one on the other side, so we've got 2 times the width times the height. And then we've got the one on the bottom, which is the length times the width, but we've only got one of those since this is an open top box. Now what we want to do, so that we are a function of 2 variables instead of 3 variables, it's going to make our lives a lot easier. We are going to solve for height in terms of length and width. So height will be equal to 12 minus length times width over 2 times length plus width. Okay, so now what we can do is we can substitute this back into the original equation for volume. So we will get 12 times length times width minus length squared times width squared over 2 times length plus width. Now what we want to do is we want to find partial derivatives of this expression so that we can optimize the volume based on length and width. If I take the partial derivative with respect to length of the volume, I get width squared times 12 minus 2 times length times width minus length squared over 2 times length plus width squared. And we set this equal to 0. We can simplify this, and we only need to care about the numerator being equal to 0. So we will take 12 minus 2 times width minus length squared equals 0. We're going to do the same for the width partial derivative. So we take the partial derivative with respect to width of the volume. We get length squared times 12 minus 2 times length times width minus width squared over 2 times length plus width squared equals 0. Again, doing the same trick with the denominator, we get 12 minus 2 times length times width minus width squared equals 0. Okay, so now we are looking at an expression where it's very likely that x is going to be equal to y, because these expressions are so similar looking. So if we set that equal to 0, we need to be equal to one another. So we get 12 minus 3 times length squared equals 0. This yields the solutions that length is equal to 2, width is equal to 2, and height is equal to 1. if we solve and plug that into this equation here. So we can solve for volume by plugging into the very original equation. The volume is a function of length, width, and height. We get the volume maximum is equal to 2 times 2 times 1, which is 4. So that's the maximum volume. Now, of course, you could have solved this using the second derivative test given these values here, or given these equations here. You could have solved for the, you could have used the you could have used the second derivative test, but it makes physical sense given that these are positive, that you would get this as your maximum. But you could have used the second derivative test to confirm that. All right, in the next video, we want to talk about absolute maxima and absolute minima. So we'll discuss that in the next video, and we'll see you then. Thanks for watching. Bye.